So you guys, we ended right here. Everybody should have got through parallel circuits. And so let's just recap a bit to make sure we're on the same page. Everybody would have built the circuit like this, right? And the main difference between the series and the parallel is all the lessons about the parents handing down the $12 and it having to be shared amongst the 3 siblings. Remember that? Remember on parallel, that's not necessarily the case because look, each of the loads, these are the siblings, have their own pathway to the parent's bank account. So you get 12, you get 12, you get 12, right? Everybody who has access is going to get 12. So like, again, understanding the parallel circuit, it kind of has some different laws. So if you were to have, let's say, this bulb go out, it's not going to affect these two because there's more than one pathway to the load. Makes sense? So those are some of the differences. But again, if we get into a problem with the parallel circuit, you'll recall, you're just going to overall understand the circuit. If you have one light bulb out, do you think it's a blown fuse? A blown fuse would cause what? Exactly, right? So first thing is just being able to understand the circuit. So if customer comes in with one tail light out and the wiring diagram is like this, you can check the fuse, but you're wasting time. You already essentially check the fuse when you notice these 2 lights work. Make sense? Then from there, you can say, well, if this light's in up, then I'm really just going to look at this circuit from here to here because that's the only point the problem could be. And then if you look at it, you're back to really a series circuit. Okay, so like I was saying, the series circuit is, understanding the series circuit is more critical than understanding the parallel because even a problem with a parallel circuit, we break it down into the series part and then we fix it anyway. Okay, so just kind of to summarize, now I'll add a problem. And this was something that we did last week. We added a resistor. Does anyone recall what the effect of adding this resistor here was? Which one? Okay.
Oh, wait, they all did.
No, they wouldn't. So now we're going to sharpen it a bit. Okay. We have 12 volts accessible. You get 12. You get 12. And this circuit right here, if you look at it as a series circuit, they have to share 12. Can you visualize it? And 6 and 6 could be correct, but I want to make sure that I'm really clear on how Ohm's law works. If this was 4 ohms and this was 4 ohms, they're of equal size and strength. Yes, you get a 6 volt and you get a 6 volt. So this will be dim. However, sometimes what happens is the resistor, this is unwanted. What if this resistance is 100,000 ohms and this one is 4 ohms? This one is going to consume way, 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 way more. And this one's going to consume just a little. So this bulb may not even light at all. And that's one of the things we get into when we have problems in the circuit. So that's kind of where we're trying to go with this is you guys understand, the series and the parallel and soon the series parallel. But if you add another load in a series, they share, right? They have to share. But this one we're kind of putting in here as if it's unwanted resistance. So if there's unwanted resistance, it can actually make the bulb go out. Now, if you were to measure it, what's really interesting, you might measure 12 volts coming in, and going out, you might measure like 11.9, 11.8. That technically means this bulb is working. It's just consuming such little voltage it won't even make any light. Basically the amperage, the current of this circuit will be so low, it's not even enough. There's so few electrons going through, it won't even light the bulb. Okay, so if we were to try to diagnose this one, customer concern would be maybe this one works and this one works, but this one's in op. You might assume it's a blown bulb. Remember, that's like back to week 1, way back in the day. You'd be like, what do you do if the light bulb is out? And you say, put a new bulb in it. And you could take the bulb out, put a new bulb in. Is it going to work? No. So what do we do? Maybe another bulb? No. Maybe 3 new bulbs just to be sure that it's not a bad bulb and a different bad bulb and another. Like, no. You really have to be able to measure that. Now, if you were to look at it, do you see an issue with the electrons? No, because you can't see them. So now that's when we'd have to measure. And that's where we get into, it's so critical to understand what the voltage should be. So one of these is what it should be. If I have 12 right here, what do I have right here? You think it should only consume nothing? This is the load. Remember that? Okay, we need a little bit of work right here. Anybody got a different answer?
0.
0 would be correct. And the reason why, the parents pass down 12 volts, they each have access to the 12. And you're going to drop the full 12. They're not sharing in a parallel. Make sense? If they were in series, they'd share, but these are in parallel. So if this is, we'll make them brake lights. If this is a brake light, and this is a brake light, and this is a brake light, all three brake lights, the left, the right, and the center, should be dropping full 12 volts, period. Because if you look, we agree, there's 12 volts. 12 volts goes through the fuse. Should we lose any voltage through the fuse?
No.
Not really. Should we lose any voltage through the wire? Not really. So we agree we should have 12 volts here. Right here, look at what this is. It's, by the way, close the switch, okay? I need to make sure you understand. When we're testing the circuit, you don't test brake lights with the brake switch not pressed. You know that, right? So you'd assume here we'd close this. If we get over to here and it's going through the wire, should we drop any voltage? Should we drop any voltage through a nice, good condition closed switch? But remember some of the laws of electricity, it should drop the entire source voltage in the circuit, so all that 12 should be dropped right here. It should go from 12 to 0, 0, 0, 0, 0, 0. Cool? Now, this one's going to be different, though, because this one, exactly, and so let's speak of it as if you do see the resistor, and then we're going to switch it to if the resistor was like a, not necessarily a component, but like a corrosion in the connector, okay? What you'd see here, would you agree that there should be 12 volts here? Okay. What should there be here?
0.
There should be if there was no resistor, but now that you see there's a load and another load, you know it's not going to drop the full 0. It's not going to drop everything. It's got to share. The question is, how much does it drop? And the answer to that is it depends on what the resistance is here versus what it is here. So let's make it simplified. I'll help you. I'm going to help you because I'm going to provide the resistance for you, which the customer would never do. So bear with me on this lesson. But let's just say this is a 4 ohm and this is a 4 ohm. How much should it drop? Remember the siblings lesson.
6.
How come 6?
Because they both have the same.
Exactly. They're of equal size and strength. So you basically have twins. So if you have 2 twin brothers, they're going to be like, I'm going to take 8. And I don't think so. We're going to fight right tooth and nail to the death, maybe. And they're going to basically drop 6. So if you had 12, they're equal size and strength. You get half, you get half. What's half of 12? It would be a 6 volt drop and a 6 volt drop. Okay. So that's how it works. Now in practical, if it's, right, this is the theory. If it's on the car, the likeliness of you having not a resistor, but a corroded connector, and it being exactly 6 ohms, exactly 4 ohms on the corroded connector, that happens to be the same as the load, is probably not likely. Let's just say you had, 4 ohms here, and you had, how about 2 ohms right here? Anybody think they know what the voltage drops would be? Isn't this one double the strength? And this one's kind of half. So this one's going to consume double the money. This one's going to consume half the money. You can fudge some numbers in there real quick.
9.
8 and 4.
8 and 4. At least you kind of understand the concept. Now see if you follow me. If this one takes 8 volts and this one takes 4, does that work? Is 8 plus 4 12? Yes. And is 8 double 4? Yes. So if it's 4 ohms, which is double 2 ohms, it means it's going to take 8 volts, which is double the 4 volts. So that was just funny math, just subbing numbers in real quick. That's Ohm's law, though. That's how you apply the Ohm's law, the scientific law that you can test over and over, and it's always the same. Makes sense? So like, there you go. Now in reality, let's say it wasn't a resistor. Let's say it was corrosion in the connector. Let's say this was a 4 ohm bulb, which would be pretty low, by the way. And let's just say this was, like I said before, 100 kiloohms. You know what that means, right? That's 100,000. Okay, so if you think of, if you make it like the siblings, right? This sibling weighs 4 pounds and this sibling weighs 100,000 pounds. Which one of those is going to be stronger, bigger, more, much more? Like exactly what this proportion is, it would be 4 to 100,000. So if this was going to take $100,000, this one's getting 4, but there's only $12 available. So this one's going to take like 11.8 or 11.9 something. You could do the math. The way you do the math, there's no real reason to do Ohm's law, to be quite honest with you. But you could do Ohm's law and you could predict exactly what the voltage drop would be. But I'm going to sub some numbers in there and you could bear with me. So this one is very small now. I'm going to say it may drop something like a 0.1 volts, which would mean if you were to take your meter, so I'll be the meter. Okay, now we're troubleshooting a problem car. I have a brake light working, a brake light working, a brake light not working. If I were diagnosing, I'd take my black lead, I put it on the ground, I take my red lead, I get a 12.0. Cool. And then I put it here, and you know what I get? Tell me. Technically not 12 anymore, though, but yeah, exactly, 11.9. And you're like, what? This thing is only going to consume 10 cents? This should take 12 volts, would you agree? But it's only consuming 10 cents. Why is this only consuming 10 cents and it's leaving $11.90 left over? Exactly. Exactly. It's sharing it with another sibling that's much bigger and much stronger, except it's like remember we joked about the secret family? Second family, you don't know like where the money's going. So this would be the corrosion. This could be something like that, right? But mathematically, I want you to just kind of understand it. And from a theoretical standpoint, I want you to understand it. So if I were to do the diagnosis and I were to get 12 volts and 11.9, you know what I know already? I know there's resistance here on the ground. Does that make sense? Where the resistance is, well, I have to do another test. How about if I were to measure 11.9? What do you think I'd measure right here? Anybody think they know?
0.
It wouldn't be 0 yet. How much am I dropping on the wire?
Like 1, so 11.8.
Yeah, 11.8, 11.9, right, about the same. I shouldn't be dropping a lot of voltage on the wire. Now, what should I measure here? 0, exactly. So if I were to measure 11.9 here and 0 here, I'd be like, oh, there's a big voltage drop right in between these two. I would know that there's unwanted resistance in there. Make sense? And then whatever that component is, I'd have to replace it. So if it was a connector, like a male-female connector, and I had 11.9 go in the connector and I had 0 coming out of the connector, I'd be like, whoa, why do I have almost a 12-volt drop on a connector? I should never have 12-volt drop on a connector. That basically means there's almost no connection between the two. Cool, so when we do wire repair, I might cut this out and put in a new connector. And if I put in a new connector, I drop the resistance, I eliminate it, and now this will drop the full 12 volts and this will glow, and then I'll have fixed the light. Make sense? That's how you walk through that. Okay, so now I'll even give you a little bit of a bonus that's not necessarily related to this, but let's just say, this is going to help you be ready for a midterm. Let's just say I had 12 here, 12.0 here, I had 12.0 here, I had 12.0 here. Anybody think they might know? Let me add. How about 12.0 and a 12.0? With those measurements, which by the way would be 1, 2, 3, 4, 5 measurements. It's kind of a lot of measurements for this problem. But let's say I had none of these light bulbs working. Does anybody know what's most likely the issue?
The switch.
It could be the switch. It could be no ground. Technically, if this ground was gone, did you know that we'd have 12 volts going all the way to wherever the open is? But yeah, most likely if it's a component, it's probably going to be the switch. So here's how. This drops nothing. Even though this has resistance, we'll change the resistance now. We'll make it a 12 ohm bulb. So this should drop 12 volts. This should drop all the voltage. But if this switch is open, how many ohms is an open? Do you guys remember? On the meter, you know it would read, right? OL, but what's that actually mean? Okay, so let's make how many ohms? 1, comma, comma, comma. How much longer do you want to go? If it's millions of ohms, now look, you have 12 ohms versus, let's say, what's this number? I don't know, like some massive number. Do you see now why this would drop basically nothing? Because you have 12 ohms and you're facing basically infinite ohms down here. If you had a full-on open, you'd drop nothing. You'd drop nothing. You'd have 12 volts coming in, you have 12 volts coming out, and you're like, oh, this is an open. Makes sense? If it started with 12 and it only dropped nothing, it still has 12, you know down here there's an open somewhere. Mathematically, we just proved it. If you have an infinite amount of ohms versus 12 ohms, this is going to take all of the voltage drop, and this will take nothing, nothing, nothing. Yes? No? So that'd be a good prediction right there. So if you were to see this on your midterm, like in a couple hours, you'd be like, oh, I start with 12, I should have 12. Right here, I should drop all 12, and this should be 0, 0, 0, 0, 0. Now, if the switch was messed up, depending on how messed up, let's say the switch was a full open, this would drop nothing and leave 12 to here. If you had 12 here available and 0 here available, that would mean the switch was open, which in this case, the switch is drawn open. But if you were to close it, it were to still have 12 going in and 0 coming out, that would tell you, hey, this switch is no good. Make sense? That's how we diagnose the car.
And how do you, with the prongs, how do you do the voltage drop again? Just to...
Okay, is it clear if on my body's the voltage drop?
Yeah.
Okay, I like that because I told you on the test there's going to be a voltage drop. So if I'm doing available voltage, everybody follow? Available, 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 available. Now voltage drop. Voltage drop, it's the short T-Rex arms. What component do you want to test?
Just so,
If you want to just, which one?
so lamp A.
Okay, lamp A. Okay. How much should it drop based on the last lesson?
And you're not unplugging.
You don't have to. Exactly. So remember, your meter measures the difference in voltage between the 2 points. So when we're checking for available, you just hang this one on the ground and you're like 12, 12, 12, 0. Cool, that light's good. Whereas with the voltage drop, you're testing between the 2 points. You're going to be like, what should the wire drop? You tell me, what should the wire drop? Nothing. Yeah, it should drop nothing. What should the load drop?
12.
Everything. Yeah, exactly. Makes sense. So like 2 different ways to go about the problem. If it's on the circuit board, available is like pretty nice and convenient because you can do it quick. If it's on the car and it's hard to find a ground and you're testing a brake light and you're like not wanting to put your black lead on the battery and then stretch and stretch, your leads are too short, you might just go to the brake light itself and be like, let me just check the bulb. Boom. It's dropping 12. Boom. It's dropping 12. It's dropping 0.1. That's not good. Make sense? So you know this circuit's good, you know this circuit's good. It's dropping 0.1, and then you're like, well, now you might need to switch to available to have it make more sense. Then you'd be like, let me do available. 12 volts, 11.9. That tells you the problem's down here. What if it was a different way? What if I got this? 12, 0.1. 0.0. Forget this being there. In fact, I can make it go away. How about that? Now what? Now what do you know? Should I have 0.1 volts going into the bulb?
No.
Heck no. So where's the problem?
Wire.
Yeah, that's exactly right. There you go. If you had 12 and you dropped to 0.1, that wire consumed way too much. You know, inside that wire, there's some mouse chewed it or something. See what I'm saying? So if you boil it down to its most simple, car comes in, honestly, we need to sell the customer what's going to fix the car. If the brake light doesn't work, we sell a bulb, we sell a switch, we sell a wire harness, we sell a wire repair, whatever. All those are fine. It just has to be the right part. You can't sell a bulb when it was this wire. You can't sell this wire when it was corrosion in this connector. You can't sell a wire repair right here when it was actually an open switch. Make sense? You're just finding out what component's bad and you're chilling. Right, so this one had quite a few little exercises we could do, but I'm calling audibles as I see fit, and I think you guys are probably pretty solid on that, I think. And if you're not, I think we need to do a little one-on-one time. Okay, so that's kind of what this was saying. Now I will give you a little bonus right here because we're kind of summarizing the theory. If I wanted to measure the resistance of this resistor right here, talk me through how do I do that?
Switch your...
Put it to ohms, click to ohms, I agree.
And then you put it right before the resistor to your XL, yeah.
Like this, boom. Yeah, and just don't forget, you need to disconnect it. Disconnect it and then measure resistance. You're like, oh yeah, it's 2 ohms. Yeah, that's it. Measuring resistance is simple. If we thought we had a bad ground, I could literally just disconnect this connector, put my lead here, and be like, how many ohms on the ground circuit? And it should be like basically nothing, 0.2. But if I had 100 ohms on the ground circuit, I would know the ground circuit's bad, right? So we mostly are going to hammer on voltage, available voltage, voltage drop, because that's the better test. But you got to be able to measure resistance periodically too, especially on this midterm. So you all been warned. Okay, cool. Now, let's go with the series parallel. And I think you're going to find this is going to be really easy to understand because we've already covered all aspects. We're just combining the two. So if you look, the reason this is a series part is because there's one path. Make sense? But like if we were to back it up to here, you might say that this is a series part and this is a parallel part. And you're kind of right because there's one lane right here. But the reason we don't consider this a series parallel circuit, this is just a parallel, is because there's no load while it's in the series part. Make sense? So it's almost like right here is a single lane. That's true. That's like series. And right here's a multiple lane highway. That's parallel for sure. But the reason it's not series parallel is because there's no load here. So watch the difference.
There's no toll.
Yeah, exactly. There's no purpose. You know, there's nothing specific. The load in series, see that? So if you had a series part with a load, whether that's a bulb, whether in this case this is actually a variable resistor, so this is a dimmer. If we put a dimmer in there and the dimmer is in the series part and the dimmer is going to drop voltage and then the parallel part is going to share the remaining voltage. It's kind of interesting, right? That's a series parallel right there. How do we diagnose it? Again, I like to keep it simple, stupid, the KISS method. If you look at the circuit overall, let's just say this bulb is out and this bulb works. What do you think the possibilities are? You think it's a bad fuse? No, thank you. But on day one, you would have told me yes, maybe. Okay, so you're coming along, good. Do you think it's a bad switch? Because we have one working, if the switch was bad, what would happen? Exactly. So we don't, you know what? Overall, if one bulb is out and one bulb is working, it's not a problem in the series part, right? Because the series part's one lane. If we have a problem in the series part, neither one of them work. Cool? So if I roll up to the car and I'm looking at the headlights and both headlights are out, yeah, cool. I'm good with the fuse, with the switch, you know, whatever. I might look in this side right here. And then, by the way, sometimes it comes back to one at the end. Make sense? Mm-hmm. Let's say that they shared a ground. It might be way down here. Now, headlights, it depends on the system. Sometimes the headlights have their own ground, right? But that's why we got to pull the wiring diagram and see how it looks. In this case, they come together and they share a ground. So if neither one are working, it could be here to here, or it could be here to here, technically. Okay? Now, let's say I take a step back and I look, and one works and one doesn't work. Am I worried about up here?
No.
Am I worried about down here? I'm really worried about, I forgot which one didn't work. Okay, this one doesn't work. I'm worried about here to here. Would you agree? So guess what? It's not really any different than a parallel diagnosis. It's really the same. The reason it's considered different is just because this load, here's basically the only time you're going to experience this. And, you know, if you're working on a new car, actually, you're not going to experience this at all, to be quite honest with you. If it's an old car, you guys ever get in, you turn the headlights on, you look at the instrument panel, right? You know you can make that bright or dim? This is how. You have 12 volts, you turn on the lights, it passes 12 volts through here, and if this was not here, you'd have full brightness, really bright instrument panel lights, interior lights, the little radio night lights and the knob lights for the HVAC and all that. Cool, but let's just say you're going somewhere and you have to drive. It's non-daylight savings time. It gets dark at 5 o'clock, which is a nightmare, and that was not my idea, but I support being permanent daylight savings time for the record. Now, if you were to want to go somewhere and you're going to be driving for 5 or 6 hours at night, do you want these really bright lights all that time? No, so let's dim them. How do we dim them? We add a load in the series part, and the more resistance this has, exactly, the more dim. So if we were to say, I'm not drawing on the canvas thing. I'm going to put it up. It's going to be safe. Way up on there. Way up there. Let's just say I were to do we'll keep with some of the resistances we've been using. A 4 ohm right here. And this is a 4 ohm. And this is a 4 ohm. Now we could draw it out. These both have access to the leftover money, right? But if the parents pass down, hey, here's $12, and these are basically going to be, like, for simplicity's sake, this isn't actually 100% mathematically accurate, but let's just say if this one's 4 ohms, and this circuit down here is 4 ohms in total, so I'll actually simplify it. I'll make this part 4 ohms, okay? What are we expecting to drop for voltage here? This has 4, and these two combined have 4.
6.
Exactly, so we would have 12 volts coming in, the switch is closed, 12, 6, which means these both get access to the 6. These two don't share the 6, it doesn't become 3 and 3, right? And that's where it's a little bit weird, because right here, it's series. And in series, it dropped 6 volts, so there's 6 left over. But right here, it splits to parallel, so they both have access to the 6. You see how that's a little different? So you get 6 and you get 6. Now that looks kind of weird because you look like you're dropping 18 volts, but that's why that's why we have to cover this slightly differently.
Do they count as one? If they're connected like that, the resistance is not, it's just 1. They don't add up, like the bulb is like 2 and 2. Like,
remember how we started to do that math on parallel circuits?
yeah.
That's what you have to do right here to really know. So I want to simplify it, and I want to say, if you were to have both of these, that would mean actually these are more than 4 ohms. These might be like 6 ohms or something, but combined, the resistance becomes 4. So you could look at it like this, like, if this whole series part of the circuit is 4 ohms, and then the parallel part of the circuit is 4 ohms, they'll split at 50-50. So if you really want to figure it out, you'd have to do that parallel circuit calculation to determine how many ohms this is. But part of the reason that I shy away from that is because I would never do that. You might do it. Maybe.
It's 8 ohms on both to get 4 ohms in parallel.
See, that's why you're the man. Okay. Okay, I like it. I like it. Now, if we were to do that, let's go like this. Let's say what you were experiencing was your bulbs were, both your bulbs were dim. Let's say the customer rolls in and all these bulbs are too dim. You're probably at no point going to be like, stop, let me do the Ohm's law. You know what I'm saying? So like the last time I did Ohm's law calculation was I was pretty much in your seats. I was like in school. The whole purpose of Ohm's law for technicians is so that we can understand and predict. And you can see that's actually more challenging than you think. You look at this and be like, who's going to drop what now? And you don't really know, right? So that's why we need to have Ohm's law. You get 6 volts, you get 6 volts. Let's say it's a little more practical. Car comes in, it has dim bulbs all the time. All your instrument lights are dim. This instrument panel, your radio, everything is dim. And you go to the dimmer and you turn the dimmer all the way up and you turn it all the way down and all the way up and all the way down, and they're still too dim. What are your thoughts? What are your thoughts? Do you think it might be this bulb? Because would this bulb make the other bulb dim? Right? Because these are in parallel. They have their own access to the voltage, so that would be a no. So if the lights are always too dim, you're kind of like, well, if both lights are affected, I think it's going to be in this part of the circuit. And if you weren't exactly sure, yeah, it's in the series part. If all the loads are affected, it's going to be in the series part. So what you don't want to do is be down here troubleshooting this. When both of them are dim, you need to really be troubleshooting this. Make sense? So once again, you're going to evaluate the circuit and be like, if this, let's say the instrument panel lights work, but the radio lights don't work, then you're troubleshooting here. Make sense? You're troubleshooting the circuit that's specific to the radio lights. But if all the lights are too dim, I don't really care about right here. I care about right here. Make sense? At which point, if you're diagnosing between here and here, what type of circuit is it?
Series.
Exactly. So once again, you're diagnosing a series circuit. A lot of times you're going to just have to do an overall understanding of how the circuit works, a little bit kind of how Ohm's law is applied without doing the math, and just evaluate, am I troubleshooting here to here? Am I troubleshooting here to here? Make sense? And then you're going to break it down into a series circuit. You just got to know, is it this series circuit or this series circuit or this series circuit? It's got to be one of those. And technically even this series circuit if you want. It's got to be one of those, call it 4 circuits there. Kind of make sense? You think you could do it? I think you're going to figure it out. All right, pretty good. So that's your series parallel kind of introduction. We could do a little bit more work on that, but I think you'll find it somewhat redundant. So here we go. Let's say 12 volts from the battery. If you wanted to measure amperage, for example, depends on which point. So when you want to measure amperage in a series parallel, we actually treat amperage like current, really like a parallel. So if you want to know why the fuse is blowing, the current that's relevant is the part in the series circuit. Make sense? If you want to know why the bulb is dim on the left, then you'd want to measure current right here. So I'm gonna put this back up. Let's draw some numbers. Let's see if you can pick up what I'm putting down. If I have 1 amp and I measure it right here, right? I break it and I send it into my meter. That's a 1. It's an ugly 1. And I even use the right wire colors. I send it down into here. And this is my meter right here. And I get 1 amp. And then over here, I get another 1 amp. I tie it in. This lead needs to actually be connected. You guys can see how many amps over here?
1.
How many amps over here?
1.
Let's see if you get this. How many amps right here?
2.
Yes, 2 is the answer. Think about it like traffic. If you had a single lane road, there it is, and you can't see the single lane road, but then the single lane road splits into 2, and you're down here at the 2-lane road, and you're like, oh, there's a car and there's a car. Well, how many cars were there back on the single lane then? Both of those cars were in the same lane, so there was 2 cars, right? So whatever the amperage is here is going to split and go here. Now, if it's 1 amp and 1 amp, by the way, that assumes that these have the same resistance, just FYI. If you wanted to, in automotive, I'm not sure that we'd ever really do this, but if you wanted to get like kind of tricky and you were to have like 2 amps over here And 1 amp over here, how much was there up here? Exactly. See, it's not even that complicated. It's pretty simple. Why you'd really want to measure amperage on this? I don't know. It'd probably more be like if you have a fuse that's blowing or something. Or the other reason you might measure this is we're back to that truck story. The trucker comes in and the trucker's like, hey, I added this light and I added another light and now we have a and now we have a and if we had, let's even make it, let's make them 2 amps in each spot. If I had 2 amps and 2 amps and no extra lights, how much did I have here? Let's say this is a 5 amp fuse. 4 amps okay, right? It's getting close. I think it's okay. Then the truck driver adds this bulb and this bulb, and now you have 2 more amps and 2 more amps. Do you understand? If you're adding loads in parallel, that's going to reduce the resistance. That's also going to increase your amperage, right? It didn't increase it right here. It didn't increase it right here. These stayed the same. But how many amps you got here now? 2, 4, 6, 8. Make sense? Now you just did 4 lanes. So if you have 2 cars and 2 cars and 2 cars and 2 cars, that means back here you had 8 cars. So if you have 8 amps, what's up with that fuse? It's blown. So what do? Don't you dare say that. Yeah. No, we definitely do not at all put a bigger fuse in. Because remember, if the fuse is 5 amps, this wire's probably good for 6 amps, 7 amps maybe, not 8. You know what I'm saying? So like, if now you have a 10 amp fuse in there, you're like, oh, I got an upgrade. I upgraded to the red fuse. The red fuse is high performance. Exactly. See, exactly. So now we're tying it back to what we covered before. That's why something like this is kind of critical. Now, here's one crazy thing that you could do, though, if you're the truck driver. If you wanted to have 4 lights in your trailer because you want to look cool at the truck stop or whatever, if you were to put a load right here, you could actually increase the resistance right here, which would decrease the amperage in the series circuit, which would technically decrease the amperage right here. You'd have 4 bulbs in there, but they'd be 4 dim bulbs. And you could keep it under 8 amps. It's kind of weird because remember, we're on series parallel, so this is a load as well. So if you were to look at this, well, I think you kind of get what I'm saying, right? We're really basically looking at a series circuit when we're measuring amperage. In a series parallel, it's the same as a series. It's the same as a parallel circuit, right? So measuring amperage in a series parallel, same as measuring it in a parallel. There's going to be some number of amperage at the individual legs, and the total of all the individual legs is always going to equal the series section. The only difference is we add a load, but that doesn't change our measurements really. So it's not real complicated. On a brand new car, you will do none of this at all. And the reason for that is, on a new car, it's LEDs and they're computer controlled. So if you have, let's say it's the latest and greatest car, anybody ever notice on the brand new cars, there is no real instrument panel gauges. It's an LCD screen, liquid crystal display. Well, if you want to make that bright or dim, that's all done through transistors and through pulsing the LEDs on and off, like a pulse width modulation or a duty cycle. So we no longer have any use for the series parallel anymore at all. In a house you do though. In a house, if you have 10 lights on the ceiling and you want to dim them, you would put the dimmer in series and then the lights would be in parallel. But on a car, we don't do that. On a new car. On an old car though, yes. Okay, so if you were to look, let's say the voltage drop, for example, you got 12 at the source, you might drop a tiny little bit at the fuse, you might drop a tiny little bit at the switch, which is now closed. How much do you think we should drop at this? Not a tiny bit, right? That's a load. But should we drop all 12 volts though? Because if you drop all 12 volts here, what is with these bulbs? They'll be out, right? So we're never going to drop the full 12 volts right here. But if we were to drop 4.7, that would leave 7 volts and 7 volts, right? Because 4.7, 4.8, 4.9, and then down here we're dropping a volt, so that'd be 5. So if we're dropping 5 volts in all the series areas, and we started with 12, that means there's 7 left over for the load. You get 7 and you get 7. Make sense? So we're going to drop something here. Now, if you wanted to test this dimmer, in the unlikely event you're working on an actual series parallel circuit, if you wanted to test this dimmer, you could test available voltage. You should have 11.8 or so coming in, and then coming out, you should drop some number. How much? Well, this is a variable resistor. So you guys actually have seen in your circuit building, there is a variable resistor in there. So the variable resistor does exactly that. It varies the resistance. So if you were to turn the variable resistor all the way down, it should drop very little. So all the way down, maybe it drops a half a volt. Exactly. It's almost like it's not open or closed, but it's almost like very little resistance or a lot of resistance. It's kind of funny if you think about it. So it's a load, but it's a load that can vary. So if you have very little resistance, it'll drop very little voltage. And you might have 11.7 to the lights. Those are going to be pretty bright, right? If you turn it to halfway, about what do you expect it to drop? Half the voltage. There you go. So if you had it halfway, it might drop 6 volts, and you might have 6 volts for the lights. And then if you turn the resistance up, it's going to drop more volts, which means there's going to be what available to these? If this drops more, here there's going to be less, exactly. Right? So that's it. We're just going to vary right here. This resistor, we can vary this resistor. A lot of resistance, a little resistance. Depends on what you want. You want bright or you want dim? Huh?
So for those right there, the volts stay the same for the loads, right? The volts stay the same, so the amps are the ones that change, right?
Kind of. I'll explain it my way. The reason right here that these stay the same is because they both have access to the same, because they're in the parallel part. But right here, as we change this, consider these are like a team. If these are the same type of bulbs, they're always going to drop the same amount. And this has to share whatever's left over. Right. Cool? So if we add resistance here, we're going to drop more voltage. These are going to both have access to the same amount, but it's going to be less for both. Right. So if we're changing you got an interesting point. If we're changing the variable resistor, from now on we could call this the dimmer. Let's call this the dimmer because it's pretty much going to be a dimmer. If we change the dimmer, it is going to change the amperage here, which is going to affect both of these equally and the same. Make sense? Because they both get their cars or their money from the same pipe. If it was water, okay, if this is a sprinkler and this is a sprinkler, and you lower the pressure in the main pipe, both of the sprinklers aren't going to spray that well, right? They're both going to be not having enough pressure to really spray. Cool? What if, however, we were to add resistance right here? Think about that. If we were to add resistance here, that would slow this side down. It wouldn't necessarily slow this side down, though, which would mean this one would be affected, but only like half. So if we were to have, let's say, let's go with 2 amps right here. I'm going to change colors. If we go with a 2 amps right here, and this one was supposed to be 2 amps, but it got a little extra resistance in it, and it dropped to 1. What's the effect on this series part? What's this going to be now? 2 here, 1 here, 3, exactly. Whereas if we were to fix the resistance problem and we were to make it 2 amps and 2 amps, now what's the amps right here? 4. So see how, like, if we have a problem here, it'll affect here, but it won't affect here. Right? Because this has its own pathway. Here you are on the road, you're going down the road, and then the lane splits into 2. And you pick, because you're a good driver, the right lane because that's the slow lane. Am I right? Oh, no, I remember. You pick the left lane because you want to go fast. I should have known. There you are, you get in the left lane, you're like mobbing, and then all of a sudden a bunch of traffic builds up in the right lane because there's a bus, and the bus is picking people up. Does the bus in the right lane really affect your left lane?
No.
It shouldn't. I mean, it kind of does, though. In reality, people are like, oh, let me slow down. Look. It's like, hey, they're in that lane. Let's do our thing here in this lane. See, electrons don't overthink things. They just do. So if you mess up this lane and slow it down to a 1 amp, this lane should still go full speed at 2 amps. This lane is independent of this lane. Make sense? Whereas if all of a sudden you put the slow bus up here and it was supposed to be 4 amps, but you add resistance and now it's only 2 amps, and this was supposed to be 2 and this was supposed to be 2, can you pull 4 amps out of 2 amps? No, so you get 1 and you get 1. Both of those lanes are going to be slow because the lane feeding them is slow. Does it kind of make sense? A little bit, maybe. So that's the sort of like the current, how you really measure the current. We are focusing mostly on voltage, and voltage is where we do most of our diagnosis. And so we did have a worksheet. You guys didn't maybe finish this one, but we will. So I'll just walk you through what we'll be doing. 12 volts coming in, 12 volts going out. Close the switch, which means this thing, what is this? Pot. Pot. What is pot? Anybody think they know? I'll write it out. P-O-T-E-N-T-I-O. Anybody know where I'm going? Ohmmeter, yeah, exactly. So this is like a potentiometer, like a rheostat, is sort of like if you have it really low resistance, if you have it really turned really to the left, in this example, it might be technically to the right, this will be low resistance. But if you turn it to the right, that would be high resistance. So this is a variable resistor. This dimmer, now you understand, electrically we don't call them a dimmer, but like it's a dimmer for the user, so we can call it a dimmer. We'd use maybe a potentiometer or a rheostat. That's going to affect both of these. This right here is your series parallel. This is your series. These are your parallel. This is a load, and that's why it's a true series parallel. Then these are the bulbs, okay? So there is a couple of little activities right there, but it's kind of the same as what we just covered. So let's say that you have this turned down to, let's just do an example. Let's say it goes to 0 ohms. Okay, let's say you turn that potentiometer to 0 ohms. Follow me on voltage available. 12 volts, would you say? 12 volts. How much here? I have it drawn closed. 12. Going in, coming out. I turned this to 0 ohms though.
12.
Exactly. See, you got me. 12. How much here?
12.
How much here?
12.
How much here?
0.
Here.
0.
Yes, you got it. Now, what if I change it? Let's go with 2 ohms. 2 ohms, but I'll make this more simple. These two combined, let's have them be 4 ohms. This one right here, let's turn it to 4. Okay. 12.
12. 8.
Going in. Coming out.
4.
We got a big disagreements. So we're going to break it down. 6 is the answer. That's true. But I want everybody to be saying 6. I want everybody saying 6 first time. You can throw numbers out there, just seeing which one I react to, and then for a third 4 or 8. Okay, here's how. This is 4 ohms, and these combined are 4 ohms. So if this is like money, it's half, exactly. And the available voltage was 12, so you get half, and you two both get half, which is kind of weird. But if you were to just look at the parallel part and just for a second, just kind of like think of these as one load because they're combined 4, and this is combined 4. You take half and you leave these two half. That sort of makes sense? Kind of, sort of? All right, but then if you were to break it down from there, if this one took half, so we agree it had 12 coming in, it has 6 coming out. But see, look, it has 6 right here, but then it has a wire coming down here. So this also has 6. And then this being its own load and its own load is each going to consume all of it. We're going to have 0 and 0. Okay, see how that one's just a little different when it's a series parallel? Yay or nay? Stuck on that one, kind of, sort of? All right, then let's make it even worse. Okay, how about, actually, I'll keep it like that. 4, 2, 2, and we turn the dimmer up to 8. Okay, now let's talk this through. Erase our voltages. How much? 12?
12. It's open, right?
It's closed. I tried to draw it. It's closed.
8.
Forward coming out.
So I see where the confusion is. 8 ohms doesn't mean it drops 8 volts. 8 ohms has to be compared to this. And is this double? No, this is half and this is double, right? So whatever the number is, however much this drops, it has to be double what this is. So if the available is 12 and this has to be double, this should drop. How much should this thing drop? Has to be double. This would drop 8, and that's correct. However, if we started with 12 and it dropped 8, how much is left? 4. And then how much is here? 4, 4. And how much is after?
0.
And how much is after? Now here's the difference. These now are consuming 4, but you remember on the last example they were consuming 6? So if they're only consuming 4, how is their glow? How's their aura, if you will? It's not that good aura. They don't have that great of an aura. How do you say, help me with that? Your aura is weak sauce or something. Your aura is not skibbity or whatever. You see, am I right? Or no? You can, no? How would you say it? Your aura is weak? Zero, no aura, like low aura. 0 aura, negative aura. Bad aura, good aura. Bad. You know the only negative of this though? When this is consuming now 8 volts, it's consuming $8, if you will. What's the aura of this thing? It's not giving you any glow. It doesn't give a glow up. It's not even risen or whatever. Not like risen like Easter's coming, but like Riz, like not Ritz. This is consuming 8 volts, but you know what it does? Basically nothing. We put a resistor in. Come on, you get confused. Let me just explain though. This dimmer, all it does is take that the voltage it consumes and makes it into heat. So it kind of sucks because this is taking electrical voltage and make it into heat, and these are just glowing dim. But remember, when you're on that long trip, that's what you asked for. You're like, these lights are too bright, just make them dim. Cool, we could do that. We'll put a potentiometer in there, and the potentiometer will consume the voltage and make it into heat. And that tends to be the failure point, by the way. These tend to get hot and fail with their carbon pile or whatever they're using. And that's one of the reasons that the new cars going to LEDs makes a lot of sense in a lot of ways, but one of the things is they're just more efficient. So rather than burning this off as heat right here and then having these be dim as a result of sharing with this one, we'll just pulse the LEDs less. The LEDs won't get pulsed as much, and then therefore they'll be more dim.
Why is it so bright compared to the other lights?
It depends on how you define bright. So if we want to get into lights, which we'll talk some about lights, but you're talking about like lumens. Lumens is like the amount of light, or you might also be talking about like the frequency. So like the whiter light tends to be more like blinding. You know, it kind of depends. But the cool thing with LEDs for the driver is you can use less amps to make more light. But there's going to be, in an LED headlight, there's a bunch of LEDs. There's not just one LED. There's like chipsets of LEDs and LEDs and LEDs. Yeah, multiple. Yeah, for sure. And then if you really want to get high tech, you can get into like, they have laser headlights too. Lasers are pretty wild. I don't know that they're really in very many productions, but it was like some that they were looking into. But Beamer did have some out in at least one of their cars. Cool. So considering that, that's good. This gets a little more intense, and so this is just really using a different type of switch. So this is a type of switch where you can connect these or you can connect these. And so for this one, I want to come back to this one, spend a little more time, but not right now. Now let's tie this together in a way that's, we've been covering this for like, what has it been, like 4 weeks? So let's take everything you just learned and get it to make sense on the car, because that's what you're going to get. When you the mechanic, the customer never comes in and asks for Ohm's law. They're going to come in with a problem. And you're going to use your understanding of Ohm's law to diagnose the problem. Most of the time, however, it won't be with math. So if any of you are like, oh, this math part is really fun, that's more like what an electrical engineer does. I don't know a whole lot about it other than they design it, they make it work, and then it's in the car. My job as like technician is, customer comes in with a concern, I have to understand the circuit enough to diagnose what's wrong with it, then perform a repair, then the car goes on the road. Make sense? So if you want to be if you liked the math and the engineering aspect, there's somebody you could talk to who could probably guide you in a certain way. But at that point, I'm showing you where it surpasses where I'm at. That's not what I do. That's not, never been my training, never been my thing. So now I'll get in my comfort zone and we'll apply it to, look what it says, using Ohm's law to diagnose circuits. Okay, that, yes, I got you. Cool. So here's how we justify it. Ohm's law can be used in 2 ways to help in diagnosing circuits. The first way, not my way. Perform the math to predict and verify measurements. What's that mean? Car comes in, you look at it, and you can basically see what the resistance of each component is, do the math, and then therefore be able to like predict. I should have this volts, this volts, this volts, that volts. Cool. But then what do you have to do? You have to measure it. Exactly. But see, that's where electrical is kind of fun, is like no one holds your hand. Make sense? So when you pull up the service manual, it's not like check this connector for 12 volts, check this connector for 11.9, check this connector for 0.1. Make sense? It's more like, here's the diagram. Check anything you need to check, but you need to predict it yourself, right? So you could use Ohm's law to do math, and in my head, I do fuzzy math. I'll do approximate math. I'll know approximately what it should be within a range of what's acceptable to fix the car. But like if you nail me down on the spot, like exactly how many amps should this circuit have, I'll be like, oh, I'm a little uncomfortable with this. Let me like sit down and start doing math. Yeah, you could, but commonly not really. Overall, you'd use it to calculate electrical quantities in a circuit, and it's valuable in cross-checking actual measured results within the circuit. I agree with that. I do. The calculated result can be compared to the measurements, remember, resulted from an ammeter, or let's say even volts. You can use Ohm's law to like really pinpoint the circuit. And that's why we cover Ohm's law. But additionally, this is where I'm at, using the relationships it demonstrates to guide you through the diagnosis process, which helps you to understand the relationships between volts, amps, and ohms. That's where I'm comfortable. Make sense? So if we were to look at Ohm's law, you could do remember the Ohm's law symbol, right? The V, the A, the R, or the EIR. Remember, you could do the math with that little circle and you cover up the 1 and give the number. But this is kind of like what I come back to. You remember that picture of the volt pushing on the amp and the ohm kind of tugging it up? You might consider getting that tattoo actually, because you want to know that relationship. So if I roll up to a car and it has a problem and a bulb is dim, if a bulb is dim, you know what that tells me? There's resistance somewhere, because the bulb, and how we got there is if the bulb is dim, the amperage is low. If the amperage is low, it's probably because the resistance is too high. Now there's one exception. It could be that the voltage is low too, right? But then that would be coming from the battery. And if the battery voltage is low, would it be one bulb that's dim? Now, because see, now you understand the series parallel type of thing, right? So if it's the battery that's dead, everything is dim. The windows are slow. The car won't probably start. Makes sense, right? So when I roll up to the car, I can pretty quickly say, oh, that headlight's dim. There's excessive resistance in the circuit. I still remember when I was in high school, a car came in and it looked kind of like this, because it had one bright headlight and one headlight that was kind of dim. And I was like, whoa, what's up with that car? And I remember the instructor of the class was kind of like, hey, you just go to that headlight and pull the connector out and look at it. And I was like, why would you jump? See, at that point, I was like, why did you jump to check the connector? Why aren't we like looking at other stuff? You know what I'm saying? I didn't really understand how he got to that point. And sure enough, one of my classmates pulls the connector out. He's like, oh, it's melted. And he's like, okay, yeah, we need to replace the connector. Right? So the way that my instructor way back in the day dealt with that was the bulb was dim. That means there's unwanted resistance in the circuit. Also, these bulbs were really bright and they were silver stars. And those tend to, for whatever reason, pull a little too many amps and they tend to melt the circuit. They tend to melt the connector right there. So like he had some experience, but he also understood how to use the relationships that Ohm's law demonstrates to guide you, right? So if there's excessive resistance, that means there's going to be excessive voltage drop. That means the load is going to drop less voltage, which means it's going to be dim. Make sense? So understanding those relationships is going to help you. Just evaluating the circuit real quick. And honestly, 90% of the time we're dealing with a circuit, you know what the problem is? Unwanted resistance somewhere. It's just, that's common. We have it all the time. Okay, and then amperage cannot exist without both voltage and resistance, which is a means of pushing the amperage, like, right? The volts push the amps. And then we also have to have a path, which is the resistance, right? So just kind of understanding those. And the key term, if the amperage is low, either the voltage is too low, could be the battery, right? But if it's the battery, what do we know? It's everything, right? So like if it's the battery that's low, all the components are going to be affected, okay? Or the resistance is too high. And this right here is where we're going to do a lot of our work, is just right here, right there. Resistance that's unwanted all the time. Happens a lot. Okay, so now when we get ready to do the diagnosis, you have to know everything that's in the circuit. If you don't know what's in the circuit, you really can't diagnose it. So your airbag example is a horrible one because we're trying to do it a little more basic. So anybody have an inoperative bulb, for example? We got a light that's out. Okay, I will make one up then. Customer comes in and they have a taillight out. Yes, probably you're just going to go up to it and you're going to just put a taillight bulb in. It's probably going to fix it, right? But let's just say you put the taillight bulb in and it still didn't fix it. Or better yet, actually, I'm going to back up. New cars, you ever seen the taillight bulbs? They're not. What are they? Big, it's an LED whole assembly. So somebody came by for like a basic problem, friend of a friend type of thing, and she had like a Tahoe, or no, a Suburban. No, I'm sorry, it was a Yukon. It was a GMC. And it had the big, nice, almost like half an Escalade looking huge taillights. And she'd say like, once in a while that thing flickers and stuff. And I was sort of like, and she said, what's wrong? And I'm like, well, it doesn't really work like that. I mean, if you have a flickering bulb, the bulb is cheap. Just take the bulb out and put a bulb in, right? But mostly those days are going away, so you know. So there's even more justification to understand this. If it's a whole big LED assembly, I could put a whole big LED assembly in there. I think those are like $400. So do I want to just do that? Now I better do some diagnosis. So if it's something that's flickering, it sounds to me like either there's resistance inside the LED circuit board, right? And there could be. That's possible. That really is possible. So if I replace the LED circuit board, then it's good, right? But could it be anything else? Connector, wire, right? What are all the components in the circuit? I don't know. That's why I pull the diagrams. Get me though? So like, if you really want to diagnose it, you got to pull the diagram. When you pull the diagram, you're going to see all the components and you're going to see what wires do what. and you're going to see what color the wires are and what positions they're in the terminal. And then if I were to really want to diagnose that, the way I would want to do it is check the available voltage to the circuit board. And how much should it have available to the LED, would you think? Talking about a load, right? How much typically would a load have if it's a taillight? Should have 12 available, right? So what if I were to probe the wire that's giving the voltage to the LED and then put it on my meter, and I were to show it shows 12 volts, but then it were to flicker, and when it flickered, it still showed 12 volts. That tells me what's wrong. Did you pick that up? Exactly. If the 12 volts is steady, but the flickering is occurring, it's inside the light. Make sense? But what if I were to have it the other way? If I were to probe it right there and I look at my meter, and when it flickered, my voltage dropped to near zero, then it's like something before it, right? So if you have something before the light, it's going to give 12 volts and then not give 12 volts and then give 12 volts and not give 12 volts, right? So like kind of what we were doing right on the circuit boards and in these diagnoses, you have to be able to apply it to the car, which is why the very next thing we cover is wiring diagrams and tracing. You got to know all the players in the game before you know which one's the problem. Make sense? So that's kind of how we do it. And then when you look at the wiring diagram, it doesn't tell you where there should be 12 volts. You have to predict that based on everything we learned over the past 4 weeks, which is kind of like Ohm's law, series circuits, series parallel, and combine that with what we covered 5 weeks ago, which was components. It's actually like 6-7 weeks ago. So like you have to know a lot of stuff to get to this point. I would have liked to have had you like on day 2 pull wiring diagrams and trace them and go out and diagnose the car, but I don't think that you wouldn't have the skills yet. So next week after spring break, you should be able to pull a wiring diagram and trace it. And then you're really just one step away from getting out on the car and diagnosing that flickering light. And then what I asked her was like, this looks kind of new. Do you know anything about the light? Oh yeah, my husband backed into a car and it bent it and broke the old light. So we got this new light and put it in there. And I was like, where'd it come from? eBay? And I was kind of like, well, and the old light didn't flicker, right? No, the old light was fine. And the new light from eBay flickers? I mean, if you want me to diagnose it, I'll diagnose it. But if I'm diagnosing that, I'm billing like, I'll probably bill like $75 an hour. And that I get it all day, you understand? So this is a very valuable skill. Instead, I'm sort of like, I don't even want to take your money. Your old light was good until you crashed it. Now your eBay light flickers. I'd probably take a look at that eBay light. No charge for that advice. Okay, and then remember, you got to know the diagram, the symbols, abbreviations, and connector stuff. So we're going to get into all that stuff in our next lesson. Cool. Now let's just say you want to do some basic diagnosis. Test lights get a bad rap, but actually it's a usable tool. I'll explain to you now that you know like available voltage and circuits, what a test light does. You clip one end of the test light to ground, and then whatever you touch with the test light is like available voltage. So if you have 12.6 volts of available voltage, your meter would read 12.6, right? What would the test light read? Exactly. So it doesn't give you as much information, but when we're diagnosing a circuit, let's say a tail light bulb is in op, I don't really need to know if the connector is dropping like 0.1 volts or 0.2 volts. Like I'm looking for something where it's dropping like 12. Okay, so a test light would be like, okay, I'm going to use this loosely. I have power because it's lit. I have power because it's lit. I don't have power. I dropped it between 2 points. I'll tell you what, I'll even back up to really nail this down. Let's just say we went to this. If I had a test light, okay, you ready? Test light glows. Test light glows. If this switch is closed, what should happen here? Test light should glow, but if the test light doesn't glow, what wrong? See, so like a test light is a usable tool, and you can buy them for $12. Okay, makes sense? But now I'm gonna, what would you say? I'm trying to get more with the times. I'm gonna throw some shade at the test light. Okay, is that, no? Did it work? I'm gonna tell you the negative about the test light. Okay, that more normal. If we were testing computerized circuits, which on a new car, how often would you suspect that is? Like almost all of them are. I'm just letting you know. The negative of a test light is when we're testing available voltage, remember where we put our leads, right? I'm going to put my negative lead down here, available voltage, right? And then my red lead I'm going to put up here. If this was a computer up here, now you have another way for the electrons. They're going to go through your meter and go to ground. Make sense? So when we're doing available voltage, we're technically adding, you see my arms? I just added another circuit, didn't I? On available voltage, I did. The thing with your meter, when you're in voltage, your meter is high impedance. That means your meter has a lot of ohms. So if I add a circuit in here, my body is the meter, but I have a lot of ohms, the computer's like, whatever, you didn't really change the overall resistance of the circuit. But a test light could have 4 ohms, 8 ohms. If I were to do a computerized circuit with a test light, remember, because we clip the test light on ground and we probe the test light over here, 4 ohms is considered low impedance. That's not a lot of resistance. I just added a full-blown parallel circuit that can kind of bypass the load. Computers want to deal like in millivolts. Remember millivolts? They want to deal in milliamps. I mean, very, very little tiny current flow. When I use a 4 ohm test light, I just made a circuit that bypasses the load that's only 4 ohms. Now, if we were to do the math, remember Ohm's law, we're going to do this. You remember Ohm's law like this, right? We'll do it right here. What goes on top? V, A, R. The volts is 12. The R, I'm saying I have a 4 ohm test light, so I'd make this 4. 12 divided by 3 amps. Your computer is not happy right now. Your computer wants to deal with like 3 milliamps, not 3 0 zeros, not 3,000 milliamps, which is 3 amps. Make sense? So that's how you let the magic smoke out. So test lights are a good tool. I feel like it's worth, discussing, but going forward, as things are more computerized, you just got to remember when you hook a test light up, you're potentially overloading a computerized circuit. What if you're working on a classic car? Test light's great. Just ask my dad. He'd be like, get the test light out. I'm like, no, Dad, let's use the meter. He's like, I don't know how to use the meter. That's okay. I'll do this. Just settle down. I got this. Computer, no test light, no computer. Test light's fine. I'm good with a test light. Okay, so here's kind of like showing you how to do it, right? Testing fuses, for example, that's all legit. You could do it. Okay, now another tool, as we talk about it, jumper leads. Okay, did anybody do any kind of jumper stuff when we were troubleshooting the boards? Because a couple of you had some bad components. We did some jumper leads and stuff, didn't we? Now this says fused jumper leads. In a jam, sometimes I'll use unfused. You understand what the negative of unfused is, right? If I were to go back to that other page that I was just on, right there, and I were to use a jumper, let's say right here, if I had my jumper lead down here and I was like, yeah, let me jump the switch, and I jump it like this, I just bypassed all this and I just blew the fuse. Okay, so a jumper lead can be very useful, but we especially have to be concerned if, let's just say, we're working on a circuit where maybe it's unfused in the car, or maybe it's a really big fuse. Like, yeah, and airbags, there's a whole side lesson on those. So with a jumper lead, it's helpful. Like, for example, if we had 12 volts, 0 volts, and the switch was closed, do you know what's wrong? 12, 0, 0, 0, 0, 0, 0, 0, 12, 12. The switch is no good. But let's just say I want to double check myself. I could use a jumper and I could hook here and bypass the switch. That's what a jumper does. Now and that's part of the reason I'll sometimes use an unfused jumper, is because it's already got a fuse. But if for whatever reason, let's just say my jumper was like was a small wire, and there was some sort of a short or something, I could actually overheat the jumper wire. It's just safer to use a fused jumper. If you jump the wrong things, it pops the fuse in your jumper. So that's kind of what it's showing back there. A jumper lead is a good tool to do diagnosis, but you got to know where you're jumping, and it's a better idea to have it fused. And I would probably have it fused with a pretty low amp fuse. Okay, that way you're not, once again, we're especially concerned about computer controlled circuits. When you're probing the wire outside of the computer, it's still connected to the inside of the computer with the small printed circuits. Remember electronics? Cool, so it's a good idea. Another thing you could do, extend connections to allow circuit readings or test with your meter. So remember we were saying, like, you want to check available voltage back at the tail light, but the battery's at the front? Well, a jumper lead will fix that, no problem. You could make a jumper lead, use an alligator clip, use a fuse holder and a fuse, and use as much wire as you want. You can make 50-foot jumper leads if you wanted. You got to wind them up afterwards, so I don't know about all that, but you could. And same if we're doing oscilloscope, whatever. It's a way to extend our test leads. And then there's quite a few tests we could do with the jumper lead, basically bypassing circuits. Okay, now here we go. Let's talk about locating open shorts, bad grounds, high resistance, because that's what we've been spending like weeks and weeks on. How do you locate them? So an open circuit, you know what that is? It's a break in the electrical circuit. Could that be a wire?
Yeah.
What else could it be though? The switch, could technically be the load, could be the fuse, could be a connection, could be the ground, right? So we don't know what component it is. We just know, like, hey, there's an open in this circuit. How do I know? Because the bulb is out. So like if the bulb is out, there's an open. Could it technically be a high resistance? Yeah, but it'd have to be like a really high resistance. And the way we find a high resistance and an open is kind of the same anyway. And it would be the power, loosely, or the ground circuit. Most opens can be located by probing along the circuit at various points. So remember how we do available voltage? 12, 12, 12, 12, 0, 12, 0. It's right there. That's how we find it. Boom, done, just like that. Now the various test points, we got a big lesson on that. You do not go stabbing that wire all the way down the line saying like, well, that's what it said. Like, that's not what it's saying. We're gonna probe it at connectors. We're not gonna probe it in through the insulation. Okay, and then an open circuit will cause a voltage drop equal to the source. Now what the heck does that mean? Reword this for me. How do you know it's an open and not like a high resistance? What's the difference? I'll give you a clue.
The resistance won't have a voltage.
I'm thinking like this, like if I measured a component and it went from 12 volts to 6 volts, is that an open?
No, that's resistance.
Exactly. If it went from 12 volts to 0 volts, it dropped the source voltage. So like when something drops all the voltage, that's an open. That's an open right there. When something drops some of it, but not all of it, that'd be like high resistance. What's the difference? Well, honestly, it's not really a big deal. Like if you're dropping the full voltage, you probably know that the wire's actually broken. Whereas if you're dropping some of it, you probably know the wire's like partially broken and corroded. Either way, you're still replacing the wire or repairing the wire, but that's the difference between an open and a high resistance. Now let me test your memory. I told you a long time ago why I was going to be nitpicky about an open versus a short. And now we're even adding a high resistance. Remember I told you I would fix these cars and I'd write my story up, and then the service advisor would type my story up and he would be changing my word from an open to a short. Do you remember I told you that a long time ago? Now do you understand why it's a big deal? An open is an open. That means the wire is totally separate, or the connector is totally separate, or the component's completely open. A high resistance means there's a high resistance, which means it's still connected, but it's dropping some voltage, but not the full voltage. Then why do you think it was a big deal that he was changing it to a short?
Short just means that it's jumping to the easiest.
And that's what I'm saying. I was like, dude, a short and an open are totally different, man. And he's like, well, whatever. The customer doesn't know. Yeah, the customer doesn't know. But if this car's ever involved in a lemon law and I'm brought into court, they're going to look at your notes and they're going to be like, this technician's a ding dong. I don't want to be labeled a ding dong. And so I had to help him, like, give him a little feedback. Be like, hey, don't change my words. You can fix my spelling, though, but don't change my words. Okay, so this is kind of what we're saying. An open would cause a voltage drop equal to the source voltage. So if you wanted to locate an open, here you go. First, you could perform a voltage drop test on each side of the affected circuit. You could do that. You could be like, here's the load in the middle. Let me voltage drop the ground. The ground shouldn't drop any voltage. Let me voltage drop the positive feed. That shouldn't drop any voltage. You know why? Because the load should drop pretty much all the voltage. So the ground should drop very little to none, and the feed should drop very little to none, and the load should drop pretty much everything, right? But if it doesn't, then you'd be like, wait a minute. Once the voltage drop is isolated to one side, what do you think that means? What that means is, if we were to do the voltage drop, let's see if you can follow what I'm saying. We'll go with, this one will work. Although, do me a favor and like kind of ignore this. Let's just pretend it was just a parallel. If I do a voltage drop right here, and let's say I drop 0, and I do a voltage drop down here, and let's say I drop 12, what side's the problem on?
You don't know.
I do. No, let me do it one more time. Look at right here, I'm before the load. Right here it drops 0. Now I'm after, right here it drops 12.
The loads.
Not quite. Look at my leads. I'm dropping 12 between what 2 points? So the problem is on which side, the positive or the negative? Yeah, that's what I'm saying, right? So voltage drop, you could tell whether you're looking down here or whether you're looking up here. Make sense? Because remember, when the load doesn't work, it could be on the positive or it could be on the negative. Go ahead.
So the loads, shouldn't it be 0 though?
Exactly. And right here, I'm showing that I'm dropping. So see, like between this and this, it shouldn't be dropping voltage. It should be 0. I'm tell you what, I'm going to do it 2 ways for it. Because the way that the book's describing it is a voltage drop. So I'm going to do it in the voltage drop again. Right here, we should drop 0. Right here, we should drop 0. Right here, we should drop everything, 12. If we drop 0 and we drop 12, that means the problem's between the red and the black. It's a problem on the ground side. That's kind of what it's saying. Now I'll do it the way that I would probably do it. I like available voltage. I really do. If I put this here and I go, I could start up here and do 12, right? But if I wanted to be quicker, you know what I'd really do? I'd go straight to the load. I'd put the available here and I go here. If I have 12 volts here, what's that tell me about the top? It's good. Exactly. And then if I go right here and I still have 12, what's that tell me?
All bad.
The bulb wouldn't be bad if it had 12 down here. Oh, did you say all bad or bulb bad? If I have 12 volts after the load, you know what that tells me? There's an open down here on the ground. The only reason 12 volts will go through the load is if there's a bigger, much more infinitely strong resistance down here, right? This is like, these two twins are like, well, we'll only take 0.1 because there's something with like a million bajillion ohms down here. Make sense? So I like available. Available tells me a lot, but like sometimes the service manual is more like voltage drop it. And you'd be like, all right, whatever. You got to be totally bilingual. Available voltage and voltage drop. I could flip them one way or the other. 0 voltage drop. This circuit's good. 12 voltage drop. This circuit's bad. Do it in available voltage. I have 12 volts. This circuit's good. I have 12 volts. This circuit's bad. Makes sense? So that's kind of what that's saying. And how'd you know that? Well, you're understanding all the laws of electricity and how to apply them, right? And I think this is right where I was. Sorry? Exactly. It always does every single time. Whatever has the resistance will take the voltage, period. Every single time. Okay, so what it's saying is first perform a voltage drop test on each side of the affected circuit. So that means voltage drop the positive. Is it good? Cool. Voltage drop the negative. Is it good? No. Okay, then the problem's down there. Makes sense? It's just saying split it in half. So that way, you know what I don't want? And to be honest, as you know, an instructor, but also someone who provides critical feedback to techs, I don't want to see your measurements and then have you have you write in your story that you're checking the fuse. If you showed me that you voltage dropped the positive and it dropped 0 volts, you're done. Don't check the fuse. Don't check any of that. It didn't drop any voltage. Ignore anything on the positive side and get down to the negative. And if the negative has the drop, then your remaining tests should all be in testing the negative. Make sense? Technicians, it's very easy to get confused. And next thing you know, you're checking all sorts of unrelated things. Almost every time I've been in a car for too long, it's because I got confused. I still get confused, but I'm trying to minimize getting confused, and that's what I'm saying. This is a clean way to do it. Then, look what it says. Once the voltage drop is isolated to one side, work the leads closer together in steps to isolate the open circuit. So let's just say, remember the positive side had a lot more components? Let's just say the positive side dropped 12 volts. Then you could be like, well, let me check this wire, let me check the fuse, let me check the switch, right? So then you can start picking and choosing. But if you know it's on the positive, then you're gonna have to bring your leads closer and closer together till you find between which 2 points it's dropping. Then you know it's right there. And as you do that, you will isolate the open circuit, right? So we're trying to say it could be all these things. If you had a problem in the circuit, it could be, in this circuit right here, it could be this wire, this fuse, this wire, and each wire where it goes to component has a connector, right? So technically it's actually this wire, this connector, this fuse, this connector, this wire, this connector, this switch, this connector, this wire, this connector, right? So there's a lot of possibilities. You can't guess, you're gonna be wrong. I'm just letting you know, right? So we're gonna determine, if it was 0 volt drop, 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 12 volt drop at the connector coming out of the switch, then you got it nailed down. You know it's that connector, it's that male-female terminal coming out of the switch, then you could do it. Then you could fix it. Or at least sell the repair, okay? And then, this is kind of just what it's saying, if the voltage drop test on each side of the circuit's within spec, if you really wanted, you could use an ohm meter to check the load, you could use an ohm meter to check the terminals if you want, but like generally the voltage drop will tell you everything you need to know. What this is saying is, if you were to check the 12 volt, if you were to check the positive side and it were to drop 0, that's good, right? If you were to check the negative side and it were to drop 0, that's good, right? So then why is the circuit working? This should drop 0, this should drop 0. It should all drop on the load, correct? Did you know if a bulb was blown, it'll drop 12 volts across the bulb? But is the bulb good or bad? So one more step you could do is put it on ohms and then measure the resistance of the bulb. What should the resistance of the bulb be, would you say? Approximate. You guys have measured some bulb resistance. 4 ohms, 8 ohms, 12 ohms, I don't know. OL? No. What's OL tell you? The filament's open. Exactly. So you're really like, right here, if you do these steps, you're proving. Remember, here's a term I used before. You're proving that's what the defect is. You're not like, well, in my opinion, it's the bulb. It's like, hey, everybody's got opinions, buddy. You remember what I said once, maybe. Opinions are like butts. Everybody has them and they stink. Keep it to yourself. Give me the fact. Prove it to me. Show me why the measurement was at a spec, and then be like, yes, it's the bulb because this is the measurement. Make sense? If you do that, you won't misdiagnose it. And then shorts, remember? Short is a circuit fault in which current travels along an accidental or unintended route, right? So when the service advisor is writing a short, I'm like, no, it was an open. Well, whatever. No, that's totally different. A short may occur within the load, or it can be in the wiring, where a wire is shorted to ground or to supply voltage. You know what that means? We're going to jump back to that circuit for fun, and you were to look at it, and you'd be like, okay, what were to happen if the wire were to rub right here, and it were touching the ground? That is a short. And where's the load? In that circuit, there'd be none. So it'd be like positive straight to negative. Fuse is blown. There's nothing slowing down the electrons. It's going to be like really high amperage, blow the fuse. That's a short. Cool. That would be an example of a short. Oh, but by the way, it also says it could be positive too. So mostly when we're talking about shorts, it's usually short to ground. But what if you took your car to Sparky's audio and radio installations and Sparky ran that screw in through there and it pierced a positive wire and then the screw touched right here and it was giving 12 volts all the time? What would the customer concern be? Come on, think about it. All the time. You turn the headlights off and the headlights are on. You turn the headlights on and the headlights are on. You turn the headlights off and the headlights are on because it's a positive short to the circuit. Not real common, but that's still a short. We've also seen where the switch itself will become internally shorted too. Okay. It will cause lower than normal circuit resistance. A short to supply voltage may cause the circuit to remain live even after the switch is turned off. Sound familiar? So it could be either one. Okay. And then when we test it, you'll recall we test this a little bit. A couple different ways. You could use your DMM across the component terminals and compare a resistance reading to the spec. So if they say, hey, your switch, when open, should have above 10,000 ohms, and you check it and it's got 2 ohms, is that above 10,000? It says when your switch is open, it should have at least 10,000 ohms. You open the switch and you check it and it has 2 ohms. Pass or fail?
Yeah.
That's a total fail. And you'd be like, oh, the switch is shorted. Cool, I got you. That's how you'd use resistance to verify a short of a component. And then let's say the short could occur in the wire harness, are best tested by disconnecting each end of the affected wire harness, using an ohm meter to test for unwanted continuity. Let me simplify that for you, because that one's kind of tricky. If I were to go back to that circuit, my favorite one, if I were to disconnect the 12 volts, disconnect the ground, this circuit should be in total isolation, right? Should it be connected to 12 volts anymore? No. So what I do is I put my meter lead here, and I put my other meter lead to the positive, and I put it on resistance. If I disconnected it, how much resistance should there be between positive and the fuse?
0.
Not 0, because I disconnected it. Resistance. It should be an open. OL is correct. If I disconnected it, it should be OL. Make sense? OL just is open. If I disconnected it, shouldn't be open? If I disconnected it and I measure it and it shows 0.2 ohms, what's that tell me? It's still connected. Why is it connected if I disconnected it? It's because it's shorted, right? Same with the ground. I would disconnect the ground. I'd put my meter here. I put my meter on the ground. And if it's disconnected, it should be open, right? But if it has 0.2 ohms, I know somewhere these wires are shorted to ground. Make sense? That's a test that we periodically have to do, especially with sensors. When a sensor's reading is messed up, a lot of times we're measuring to see if the sensor wires are shorted to 12 volts or shorted to ground or shorted to another wire. All electrical tests. Okay, shorts are fun. All right, and then when we say like ground, we're probably talking about a short to ground. Let's just say that it was a short that was blowing the fuse. Do you remember the test I told you could do? If it's short that's blowing the fuse, take the fuse out, put a high resistance headlight bulb in, and then that would provide the resistance that the circuit would need to not blow the fuse, plus the fuse is out anyway. And then you would literally just disconnect components one at a time until the headlight went out. And that would be like, let's say it's shorted to ground. If you plugged in a bulb to the fuse, that should not light the bulb. Okay, so if we're way back here, if I were to take the fuse out, one more. This fuse should have 12 volts and 12 volts, right? But let's just say that Sparky sent the screw in here. Remember this screw? Bzzz, like that. Sparky sent the screw in there. Now this has 12, and if this is grounded, what do we have right there? Exactly. So if I take the fuse out and I put a bulb in, the bulb will light because it has 12 volts and 0 volts, right? If this bulb is glowing, you see it glowing, and I disconnect down here and it's still glowing, then I disconnect here and it's still glowing, then I disconnect here and it's still glowing, then I disconnect right here and it goes out, that tells me it's between here and here. Make sense? That's like the best way to find the short. You literally put the bulb in there and then you just disconnect things until it goes out. And when it goes out, it was after that last thing you just disconnected, but before the thing that didn't make it go out. Right? Kind of, sort of. So that's a good way to do it.
The test light, hook that screw.
Yes, exactly. It depends on how you had the test light hooked up, and if you were trying to test to see if that screw was shorted to ground, you'd actually hook your lead of your test light up to the positive battery terminal. Then everything you touch with the test light that's grounded would light it. Makes sense? Because you have your what's normally the ground of your test light would go to positive. Then everything that lead that point touches would be lit, would be ground. That screw's grounded. Oh, I see. That wire is shorted to ground, etc. Cool. So that mostly makes sense. Now here's an example of a damaged harness. So if you guys look, I'm even going to turn the light off so you can see in detail. Right here, do you see how this wire has damaged? But if you look, there's one tiny little strand still connected. What do you think that would actually cause? Is it touching the frame? Because if it's a short to ground, it would have to touch the frame. What if it was just pulled? Like it could be a short if it's touching the ground, but what if it was damaged and now it's no longer touching the ground? That would be, if there's one tiny strand,
It can't cause bad contact, right? So it's gonna like
it might flicker.
Yeah.
So this, depending on the exact details, that could cause a number of those things. One, yes, if it's touching the frame, that could be a short. Another one, if it's totally open, that's a complete open. Another one, if it's like touching and then not touching, that's causing an intermittent. What's an intermittent mean? Like it works, it doesn't work, it works, it doesn't work. What if there's one strand and it's reliably connected, but the other strands are broken off? That might be a high resistance. That could be a dim, right? So when you go about the circuit, understanding, what the symptom is, you're going to be kind of knowing what you're looking for. If this one is kind of a bad one, this one causes all sorts of stuff. If this one was just, let's say a mouse chewed it here and there's like a 4-inch section missing, that's just an open all the time. That's for sure an open. Right, so depending on exactly the condition, it could cause a number of things. And then we do have some other tools that can actually test circuit breakers and whatnot. And then we discussed this one. This was actually putting a headlamp to find a short. They do have some tools, specialized short circuit detection, like PowerProbe makes one called open or short tester. You might find it helpful. Most technicians don't usually use these. You might even do using a circuit breaker and a gauge that will actually tell you how much current's flowing through, and you can kind of wiggle it around, and if it touches the ground, the gauge would spike. It's different ways. And they'll even use sensors that'll measure magnetic field. So if you're going along a wire and there's current flow, it produces a magnetic field. But if there's a short or open, the magnetic field is kind of disturbed. So that's where some of the high-tech short and open circuit finders come in. And then I think this one you got, the short to power, right, is where power from one circuit leaks into another. Why is this so different than a short to ground? There's a major difference. It actually comes to do with this one. If this wire's bare, you can see it's shiny right there, right?
it could blow the fuses and stuff.
True, but if this wire is shiny, anything that's bare metal on the chassis, that would be a short to ground. So the ground is everywhere. Anything that's metal is grounded, right? But a short to power is kind of weird because 12 volts is usually inside of another wire, or like on the positive battery terminal. So a short to power would be pretty rare because this would have to happen to be shorted to another wire that would have to be stripped. Make sense? So if this wire is positive and this touches the outside of the insulation, there's no connection there. It's not shorted. You'd have to actually have multiple wires that are missing insulation to cause that. Go ahead.
So like a short to power would be like, for example, like the fuses that go to sound systems, the ones that are directly on the battery.
Yeah.
Would that be considered a short to power?
So let's say you guys have seen those where it's an aftermarket audio system and somebody's got to like put a big wire on the positive terminal, and then you bring it over here to the fuse. Those fuses usually come with a big plastic case. The reason they do that is because any bare metal in that big fuse, that would be a potential short. So usually they have you put it in something plastic so nothing can touch it, can fall in there, can accidentally touch a positive, right? So a short to power would mean somehow a bare wire happens to be touching another bare wire that happens to be positive. So it happens, but it's just the short to ground so much more common because the ground is everywhere in the chassis, right? Everything in the chassis is negative. So that's ground, and that's why we see so many more short to ground. Not because it's negative, just because we make the chassis negative. And that's all over. Okay, cool. I think overall good. Now let's talk about the high resistance. High resistance refers to unintended resistance caused by, look at this is important, corroded, loose harness connectors, maybe even incorrectly sized cable, incorrectly fitted terminals, poorly soldered joints. So that's a nice catch, if I'd say so. Right? There's a lot of things that cause this. A whole bunch of things that cause this. Right? So like, let's just say, for example, you work on a car and you have to test a terminal. And when you test the terminal, you use a probe. And let's say the terminal was this big, right? It was this big. And you like use your meter lead and you shove your meter lead in there. How big is the terminal now? Used to be this big, and now the terminal's whatever size your meter lead is. So how's the connection going to be with the meter lead being this big? That's unwanted resistance right there. That could happen very easily. Another example, mouse chews the wire. Now there's one strand or even if it's an open, that's unwanted resistance. Another possibility, a technician's in there doing some work or whatever and accidentally nicks the insulation on the wire. Water gets in. What happens to the copper? Corrosion, that's high resistance, right? High resistance is a thing that happens a lot. Even a more natural cause. You have switch contacts, right? We had some bad switches on the boards. You close your switch, it touches like this, right? Opens, closes, opens, closes. What if some corrosion builds on those terminals of your power windows of your car because you got the window down a lot of times because you're smoking, not vaping, but full on ashy and rain's coming in, and those terminals, they start to corrode, right? They start to corrode. That's corrosion right there. So like this happens a lot. This is very common. High resistance causes unintended voltage drop, right? So that means now your load that's supposed to get 12 gets 8, 6, 2, I don't know. It's only going to consume the proportion of the unwanted resistance. And if the unwanted resistance is really big, the load will consume less and less and less and get to the point where you go to run that power window and the power window's like this. And yours does that might be simply due to unwanted resistance somewhere, maybe in the switch, maybe in the wire, maybe in the connector, or sadly, there could be a problem with the motor too. But the way we test if it's the motor or the circuit is test the motor for the voltage drop. If your motor is dropping 12 volts and it's still slow, it's not the circuit. But if your motor is only dropping 8 volts, that means something else is consuming 4, it's in the circuit. Make sense? And so again, that unwanted resistance will cause unintended voltage drop, which will reduce the current flow. And that becomes less power, because remember, power is voltage times current. So that affects its performance. That's why your motor's slow. Or your starter too. You know, like you got to start the car. The starter goes. That could be, yes, a dead battery. But that could also be unwanted resistance in your cable, in your solenoid, in your, right? So we have to troubleshoot these things. Cool. Same with a dim bulb. And then what about if we had to locate, you could use a voltage drop test in the power and ground circuits. So let's say that you went to that starter that was performing poorly, right? It's slow crank. You could do a voltage drop on the positive from the positive terminal to the starter positive terminal. And let's just say it's dropping 2 volts. That's too much. That means your starter's only going to get 10. If your positive side, your feeding side is dropping 2 volts, you know something's wrong on the positive side. Okay, makes sense? Then you remember the steps. You'd move your leads closer together. Maybe test the solenoid. Maybe test this connector. Maybe test this cable. Maybe test the battery terminal, right? You could test the components and then prove which one's bad. Cool? And then we might even get into doing some more detailed things like if you want to check resistance, you could put resistance on your meter and you could measure the resistance, even though your voltage drop kind of tells you your resistance too. But for some things, if you really needed to diagnose it further, you could use an oscilloscope. The oscilloscope will show a waveform. The waveform can be evaluated. So let's just say it was a fuel pump and your fuel pump wasn't making enough fuel pressure. It could be the pump, right? The pump could be weak. Would we agree? But couldn't it be a voltage drop on the positive or a voltage drop on the negative? So let's say step 1, you test the positive and the positive drops like 0.2 volts. Is that good or bad? 0.2 volts on the positive, that'd be good. And then on the negative, it drops like 0.2 volts. You'd be like, oh yeah, basically the fuel pump should drop the full source minus maybe 0.4. You think it's good? It's good on the positive, it's good on the negative. So is the pump bad? Probably, but if you did an oscilloscope test, you could actually graph the pump performance and you could see in detail what's happening inside that pump. Makes sense? You could see if that pump has 8 magnetic segments and you look at your waveform, you should have 8 different oscillations on there. And let's say you have 6 and then 2 of them are flatline. You'd be like, oh, there's 2 dead segments in the pump. Like you could really diagnose this to a science if you had to, but probably like 99% of the time you're not going to have to go as far as the oscilloscope. But sometimes, you know, on a problem one you might. Cool? And with that, you guys have made it. So, any questions you got? Now's the time.